This is the fourth audio. We have already seen that norm 1, norm 2, norm infinity are norms on Rn. And each norm generates a distance. So those norms generate three distances. The distance d1, which is associated to norm 1, d2, which is associated to norm 2, and d infinity, which is associated to norm infinity. Now, the three norms, norm 1, norm 2, and norm infinity, reduce to the absolute value if you work in dimension 1. So if R equals R1, then, for example, let me choose any of the norms. Let's say I want to compute norm x1, but norm x1 is the summation of the absolute value of the coordinates. And here I have only one coordinate because x is a real number. X belongs to R, so x is a number, one number. So here you have absolute value of x. If you want to compute, for example, norm x2, so norm x2 is normally radical, and here you have to take the summation of the coordinates raised to the power 2, but there is only one coordinate, so you take radical x squared, and this is absolute value of x. So similarly for norm infinity, so the three norms reduces to absolute value if you work in dimension 1. Now, let me give you some examples. I will try to explain some of them, and I will leave the others as an exercise. So we start with the first example. The idea is to check whether these applications are norms or on Rn or not. Now, the first application is defined by n of x1, x2 equals radical x1 squared plus absolute value of x2. So of course, we know that to show that this is a norm, you need to verify n1, n2, and n3. Once one of these properties is not true, then the application is not a norm. Now, if you look carefully at this expression here, you find that there is x1 squared. So think about taking n of lambda, x1, x2. When you take lambda x1, you have to put here lambda x1 squared. So there is lambda squared here. But here, when you put lambda x2, there is absolute value of lambda, absolute value of x2. So in this term, you get lambda squared, but here you get absolute value of lambda. So you cannot take lambda as a common factor. So you have to think that the problem is in property 2. To see that, so to violate n2, to give me a contradiction, you have to give me a counterexample. So you take an example and you show me that the property n2 is not verified. Okay, so if I consider, for example, lambda equals to 2, and I consider the vector x1, x2 equals to 0, 1, then computing n of lambda x is computing n of 2 times the vector 0, 1, which is n of 0, 2, and this gives radical 2. Now, on the other side, if I want to compute absolute value of lambda times n of x1, x2, you get absolute value of 2 times n of 0, 1, and this is 2 times 1, which is 2. So you remark that n of lambda x, which is radical 2, is different from absolute value of lambda n of x1, x2. So since property n2 is not verified for all x1, x2 in R squared, then the property is not in general true, and this shows that n2 is not verified, and the above application is not a norm on R squared. Now, the second example, we also take an application from R squared to R. Now it is defined by radical x1 minus x2. So here it's easy to see that if you consider n of some vector with equal abscissa and ordinates, for example, if you put here 1 and here 1, so n of 1, 1 would give you 0. But the vector 1, 1 is not the 0 vector. So you have a vector which is not the 0 vector, And the norm of this non-zero vector is 0. This is a contradiction with the property N1, because we know that the only situation where the norm of a vector equals to 0 is when this vector equals to 0. Here we have a non-zero vector with norm equals to 0. So there is a contradiction with N1, and this application here is not a norm on R squared. Now we move to the third example. Also, we consider an application from R3 to R, which is defined by this formula. So because we work on R3, so we expect the coordinates to be x1, x2, x3. So n of x1, x2, x3 is absolute value of x1 plus absolute value of x3. And we need to check if this application is a norm on R3. So again, if I consider this non-zero vector and I compute its norm, I get that the norm equals to absolute value of 0, because the norm is absolute value of x1, which is 0 in this case, plus absolute value of x3, which is 0 in this case. So you get 0. So you have a non-zero vector whose norm is 0. And this is again a contradiction with property N1. Now, the third example, it's not actually an example, it's an exercise. This is a fundamental inequality that I will show here. So we have to show that for every xy in Rn, absolute value of the difference between norm x and norm y is smaller than or equal norm x minus y. So we can prove this by taking this two sides of the absolute value. So we start with norm x1, and you add and subtract y. After that, you use the property N3 for the norm, and you get that norm x minus y plus y is smaller than this quantity plus this vector, the norm of this vector. So you take norm y to the other direction, and you get that norm x minus y is smaller than or equal norm x minus norm y. If you make the same computation starting with y now, you will get that norm y, you add and subtract x, you use the property N3 of the norm, and you get the next identity. So when you combine this equation, this inequality, inequality 1, with this inequality, inequality 2, you will get that absolute value is smaller than norm x minus y. Now, I will leave examples A, B, and C for you. Okay, you have the solution, and I will give you the file, the PDF file of this lecture. So I go directly to speak about open closed balls in Rn.